Hello, I am Professor Steven Abbott. I'm going to talk about IGC, inverse gas chromatography, what it is, what it does, and I'm going to do it via apps. This is the first of the 4 videos on the basics. You can find the apps at my practical chromatography website, and I'm happy to acknowledge the help of ad scientists who are IGC specialists based in Mulhouse in France. So first of all, what is IGC? We all know what GC is, gas chromatography, analytical chromatography here on the left. These diagrams are from ad scientists. You inject some mixture into a column and the components come out as a set of peaks, and you identify the peaks and you measure their areas, and that's all very interesting. GC is completely different. You have the same column, but inside the column you have your unknown. You have a fibre, a powder, a polymer on an inert support. And you inject known simple solvent molecules like acetone or hexane or toluene. And you measure Tn, the retention time between this peak where an inert gas like helium comes out. That's just the void volume of the column. So you measure the time between the void volume and where the peak comes out. And you get this value Tn. And when you change the probe solvent, if you change it from hexane to heptane, for example, obviously the peak will come out at a different time. As it happens, these Tn values are of no fundamental value, so we need something else to give fundamental values to our experiments. And this is Vg, the specific retention volume. So Tn is the retention time of the peak compared to the retention time of the inert marker. It's meaningless on its own. G corrects for the flow rate of the gas through the column. And the column has a weight W of raw material. And there's a compressibility correction factor J, which is well known. So you just calculate Vg from Tn, the flow rate and the weight, and this correction factor. Vg is fundamental, but even more fundamental is the fact that the interaction free energy of the probe, delta G, comes just from RT log n Vg, where RT is the universal gas constant times temperature. So I could carry on giving you PowerPoint slides, but I want to go straight to the IGC apps. They're free from ads and trackers, they work on all platforms and inside corporate firewalls, and they're simple HTML5, JavaScript, CSS3. As I said at the start, they can all be found on my practical chromatography website. And here's the first one, IGC Basics. And this just tells you what I've described before about the differences and where Vg comes from, and it gives you a formula for J and reminds you about delta G. So that's fine. You can read about the IGC applications. This chart again from ad scientists gives you some idea that it can be used for polymers, for pharmaceuticals, minerals and inorganic compounds, surfactants, nanomaterials, planar materials. Lots of good things to read there, and there are references to 2 reviews which you will find handy. Now let's get to something more specific. The first thing we can measure with IGC is the dispersive surface energy of the material. You want to know if it's low surface energy or high surface energy, or at least the dispersive component of it. So what you do is you inject pentane, hexane, heptane and octane. In this diagram it looks as though they've all been injected at the same time like conventional GC, but in fact they are separate injections. But they all come out at different times, and you then plot a graph of the delta G, which you calculate from the Vg of each probe sample, and from the slope you can calculate a gamma SD, which is the dispersion surface energy. You need some factors, Avogadro's number, the surface energy of pure CH2 surface, and also the area of a CH2 group in square angstroms. The app does all the calculations for you. So let's say that the Vg for pentane was 2, for hexane was 4, for heptane was 8, and so forth. The delta G's are calculated from the formula, and then you have this plot of delta G versus the number of carbons, and from the slope and from the temperature you work out that it's 19.7 millijoules per meter squared surface energy. So relatively simple measurements just of a few alkanes, just measuring the retention times, converting those into Vg and then into delta G, you can calculate the dispersive surface energy. That's enough for the basics. In the second video we'll talk about some more interesting aspects that you can measure with IGC.